Thus far, we've learnt the yield to maturity as a yield measure for bonds. There are other measures of yield that can give us further insights of the returns from investing in a bond. In this lesson, we shall discuss how to calculate and interpret some other yield measures for fixed-rate bonds, floating-rate notes, and money market instruments. Let's get rolling. We're now very familiar on how to calculate the yield to maturity of a fixed-rate bond. For a 10% annual pay bond at its par value, its holding period yield for the full year is 10%. The yield to maturity is equal to its stated coupon rate at 10%. For the same bond which pays semi-annually, its holding period yield for half a year is 5%. The yield to maturity is equal to 2 times this rate, which again is the coupon rate of 10%. And for the same bond which pays quarterly, its holding period yield for a quarter is 2.5%. The yield to maturity is equal to 4 times this rate, which again is the coupon rate of 10%. How frequently coupon payments are made is referred to as the periodicity of the annual rate. So, given that they are essentially the same, offering the same yield to maturity of 10%, do these bonds offer equivalent returns to an investor? If you recall from the course on quantitative methods, the effective annual rate increases as the compounding frequency increases. Likewise, in this case, the effective yields of the bonds should increase with the periodicity. Let's verify. The annual pay bond will have an effective yield of 10% since there's only one coupon which is paid at the end. The semi-annual coupon has an effective half-year rate of 5%, which when compounded by 2 periods is 10.25%. And the quarterly coupon bond has an effective quarter-year rate of 2.5%, which when compounded by 4 periods is 10.38%. Let's apply what we've learnt. A bond fund manager is tasked to choose between 2 bonds of similar ratings to invest in for the next 8.5 years. Which bonds should he choose based on the yield to maturity? Pause the video now and work out your answer. And we're back. Finding the yield to maturity should be quite straightforward. For bond A, we first find the holding period yield for each half year using the discounted cash flow method. Remember that there are 17 half years to maturity, and each coupon payment is half the coupon rate. Solve for interest per period, and we get a holding period yield of 3.81%. The yield to maturity is simply double this, 7.62%. Likewise, we repeat for bond B, taking note that the coupons are paid out quarterly, so there are 34 quarters to maturity, and the coupon rate has to be divided by 4. Solve for IY, and we get a yield per quarter of 1.9%. To get the yield to maturity, we multiply this by 4, giving us 7.6%. Since bond A's yield to maturity of 7.62% is higher than that of bond B, the fund manager should choose bond A. Next, determine which bond he should choose based on the effective yield. Pause the video now and work out your answer. And we're back. To find the effective yield of a semi-annual bond, we compound the yield per half year 2 times. This gives us 7.77%. To find the effective yield of a quarterly bond, we compound the yield per quarter 4 times. This gives us 7.82%. Since bond B's effective yield of 7.82% is higher than that of bond A, the fund manager should choose bond B in this case. To further complicate things, sometimes coupon payment dates may fall on weekends and holidays, so there may be a delay in actual payment until the next business day. For example, the 1-year 10% annual pay coupon may be issued on 14th of July 2017, so the coupon payout should be on the 14th of July 2018. However, this date falls on a Saturday, which means that the payment has to be delayed by 2 days. Because of such delay, the actual yield of the bond is slightly lower than the quoted 10% yield. If we use the actual coupon dates to calculate, the yields are lower by a few basis points. This yield is known as the true yield of the bond. In contrast, bond yields calculated using stated coupon dates are referred to as following the street convention. The true yield is never higher than the street convention yield because weekends and holidays delay the time to payment. We've learnt earlier that government bond yields are usually quoted on an actual day count basis. On the other hand, corporate bond yields are usually quoted on the 3360 basis. The convention is a 30-day month, 360-day year, regardless of the actual number of days. Sometimes a government equivalent yield is quoted for a corporate bond. A government equivalent yield restates a yield to maturity for a corporate bond to one based on the actual convention. The government equivalent yield on a corporate bond can be used to obtain the spread over the government yield. Doing so keeps the yield stated on the same day count convention basis. Another yield measure that is commonly quoted for fixed income bonds is the current yield. It's calculated by the sum of the coupon payments received over the year divided by the flat price. For example, if an 8-year 6% semi-annual coupon payment bond is priced at 85 per 100 of par value at the end of its 5th year, its current yield at this instance is the $6 coupons in a year divided by the current price of 85. This gives the investor a current yield of 7.06%. As you can see, the current yield is a crude measure of the rate of return to an investor. It does not consider capital gains or losses, which, as you can see, the investor can realize a capital gain of 17.06% if he holds the bond to maturity. Sometimes the simple yield on a bond is quoted. It takes into account the straight-line amortized share of gains or losses for the bond. So in this case, the straight-line amortized gain per year is the gain of 15 divided by 3 years, which is 5. The simple yield is therefore 11 divided by 85, which is 12.9%. If a fixed-rate bond contains an embedded option, other yield measures are used. Recall that a callable bond contains an embedded call option that gives the issuer the right to buy the bond back from the investor at specified prices on predetermined dates. For a callable bond, an investor's yield will depend on whether and when the bond is called. The yield to call can be calculated for each possible call date and price. The lowest of yield to maturity and the various yields to call is termed the yield to worst. Let's pause for an exercise. This 8-year 6% semi-annual callable coupon bond is currently trading at 101 exactly 1 year after issuance. Determine the yield to call if the bond is called at the beginning of the 4th year. Yield to call if the bond is called at the beginning of the 6th year, the yield to maturity of the bond, and subsequently the yield to worst of the bond. Pause the video now and work out your answers. And we're back. Working out the yield to call is the same as working on the yield to maturity. Just assume that the bond matures on the call date. So in this first case, there are 4 periods to the first call date where the bond is redeemed at 102. Use your TVM calculator and we get a yield of 6.42%. For the second call date, there are 8 periods to call date where the bond is redeemed at par. Use your TVM calculator and we get a yield of 5.72%. Maturity date is 14 periods where the bond is redeemed at par. We get a yield of 5.82%. The yield to worst is the worst of all the possible scenarios to the investor. Since the second call date has the lowest yield, the yield to worst is therefore 5.72%. The yield to worst is a commonly cited yield measure for fixed-rate callable bonds used by bond dealers and investors. However, a more precise approach is to provide the option-adjusted yield. Recall that a callable bond can be replicated as a straight bond, and an embedded call option on the bond that expires on the bond's call date. As you've learnt in the derivatives course, a call option has value before its expiration. You do not need to know how to estimate the value of the option at this stage. It'll suffice for you to know that the value of the embedded call option is added to the flat price of the bond to get the option-adjusted price. Be clear that this is not the price the investor pays. The investor pays the flat price plus accrued interest, if any. The yield to maturity is based on its flat price. The option-adjusted price is just to calculate the option-adjusted yield. Since the value of an option can never be negative, the option-adjusted price for a callable bond will always be greater or equal to its flat price. This means that the option-adjusted yield will be less than or equal to the yield to maturity. This is consistent with reasoning, as callable bonds should have higher yields to compensate bondholders for the issuer's call option. The option-adjusted yield can be used to compare the yields of bonds with various embedded options to each other or similar straight bonds. Let's move on to floating rate notes. Recall that the coupon rate on a floating rate note is the reference rate, plus or minus a fixed margin. Notice that the current reference rate is used to set the coupon rate for the subsequent payment. We say that interest is paid in arrears. The margin is fixed based on the credit risk of the issuer, relative to the credit risk of the reference rate instrument at issuance. This margin that is fixed at issuance is called the quoted margin. For example, a 2-year $1,000 par semi-annual pay floating rate note can have its reference stated as the 180-day LIBOR rate. At issuance, the 180-day LIBOR is 2%, and the quoted margin for this issuer is fixed at 1.7%. So at issuance, we already can determine the coupon rate that will be paid half a year from now, and that is 3.7%. At the next reset date, 180-day LIBOR has risen to 3%. So when we add the fixed quoted margin of 1.7%, the coupon rate for the next payment should be 4.7%. The question at this point is, how do we value the FRN at this point? Thus far, we've been using the method of discounting all future cash flows to the present and sum them up. However, in this case, we do not know the values of all the future cash flows yet. A simplified FRN pricing model is to fix all the future coupons at the most recent rate, which is the latest 180-day LIBOR plus the quoted margin. The same principle applies. Sum up all the future cash flows discounted to the present. The discount rate to apply is the latest 180-day LIBOR rate plus the discount margin. Now, what is the discount margin? The discount margin is the same as the quoted margin at issuance. That is, the credit risk of the issuer relative to the credit risk of the reference rate instrument. In this case, however, the margin is not fixed. The discount margin at issuance should be the same as the quoted margin, but as time goes by, the credit risk of the issuer would have changed. So, for example, the credit risk of the issuer may have improved such that the discount margin has narrowed to just 1.4% after the first coupon payout. We shall therefore use a rate of 4.4% to discount the future cash flows. So to calculate the value of the FRN, we have 3 periods to maturity and an interest per period of 2.2%. This is half the discount rate of 4.4%. Payment per period is $23.50. Remember again to halve the coupon rate. And FV of $1,000. Solve for PV and we get a value of $1,004.31. Let's move on to the last segment. We've learnt that money market instruments are short-term debt securities with original maturities of 1 year or less. Such securities include government issues, most notably US T-bills, commercial paper, short-term debt issued by corporates, and certificate of deposits issued by banks. The yield measures and quotes for money market securities differ a lot from the bond market. Yields can be stated as a discount from face value or as add-on yields and can be based on a 360-day or 365-day basis. US T-bills are quoted as annualized discounts from face value based on a 360-day year. Commercial papers are usually quoted on a 360-day basis. As we've learned earlier, US commercial paper are quoted on a discount basis, but Euro commercial paper can be quoted either on a discount basis or add-on yield. Certificates of deposit are usually on an add-on yield basis. They may either be quoted on a 360 or 365-day basis. Regardless, almost all money market instruments are quoted based on simple annual interest. This is one of the major differences that distinguish money market instruments from bonds, which are quoted on a compounding interest basis. Using each of these types of instruments as examples, we shall learn how to calculate the actual payment given its quoted interest or yield, and to compare the yields on two securities that are quoted on different yield bases. Starting with a US T-bill, let's assume that there is a $1,000 par 90-day T-bill with a quoted discount of 1.4%. The discount rate is quoted on an annual basis, so we have to divide the interest by 360 and multiply it by 90. The discount at issuance is $3.50, and the issuance price is $996.50. As the interest is quoted on a discount basis, it may be useful to know its equivalent add-on yield. To find that, we simply divide the interest with the price at issuance, giving us 0.351%. Note that this is on a 90-day basis, so we annualize it by multiplying it by 365 over 90. The equivalent add-on yield for this T-bill based on 365-day convention is 1.424%. Next, we have a hypothetical 90-day commercial paper, also with a quoted interest rate of 1.4%. The difference here is that the interest is on an add-on basis. This means that the interest is given on maturity. The interest is again an annual rate, so we multiply it by 90 divided by 360. $3.50 of interest will be given on maturity. This add-on yield of 0.35% is for the 90-day period. We can annualize it by multiplying it by 365 over 90, giving us an equivalent add-on yield on 365-day basis of 1.419%. And again, we have a hypothetical 90-day certificate of deposit with the same quoted interest of 1.4%. The difference here is that it is quoted on a 365-day basis. When calculating the interest, remember to use 365 days as a base, so the interest is slightly lower at 3.452. The quoted interest is already on an add-on basis on 365-day convention. Therefore, we do not need to make any adjustment. So, as you can see, while all three have the same quoted interest of 1.4%, the actual yield when leveled to the same basis can be quite different. In the exam, be sure to be able to convert quoted interest from one basis to another in order to make such comparisons. Another comparison is to compare the interest rates to the yield to maturity of a semi-annual coupon bond. This is known as the bond equivalent yield. We shall use the example of the commercial paper to illustrate the method. Before we begin, let's first state the basic assumptions of the semi-annual bond. Firstly, the yield is quoted on a compounding basis. Second, the day count convention is 365 days. The general framework to obtain the bond equivalent yield is to convert the money market securities holding period return to an effective semi-annual yield and then double it. We've already calculated the holding period return. The add-on yield for the 90-day period is actually the holding period return. Our next step here is to use this to find the effective semi-annual yield. It's a bit tricky here. In order to do that, we first calculate its effective annual yield by compounding the holding period factor by 365 over 90 days minus 1. This gives us 1.427%. We then get the semi-annual yield by compounding it by half. This gives us 0.711%. And the bond equivalent yield is simply double of this, which is 1.422%. And that concludes this topic on yield measures. In the next lesson, we shall learn the maturity structure of interest rates. See you again.